Thanks everyone for coming today to the AFMS seminar for this week. So it's my pleasure to introduce our speaker, Dr. Woutijn Baars, who's an assistant professor in the Faculty of Aerospace Engineering at Delft, University of Technology. So he received his PhD from the University of Texas at Austin in 2013 and has also spent time as a research fellow at the University of Melbourne. His research is focused on turbulence, in particular wall-bounded turbulence and the aeroacoustics of turbulent jet flows in rotor systems. And today he's going to be talking about spectral properties of turbulence kinetic energy in turbulent boundary layers. All right, you can go ahead and begin.
Okay, thank you, Kat, for the introduction. And I first wanted to thank, I think Julio actually invited me for this seminar, but also all the other attendees here for listening to this talk, either live or I saw they were being posted on YouTube. So I think that's a great way to reach even a larger audience. I'm not sure how interactive this seminar can be. I'm not following a chat or anything, so I'm just listening to what I hear. So if you have any questions or pressing questions, just feel free to interrupt, and then we can hopefully make it a bit interactive. So in this talk, I'll focus on spectral properties of the turbulence kinetic energy in, I think, this online setting now that we're all way too familiar with. So here I have a quick outline of the talk. So first I'll start with a relatively long introduction, a little bit on wall turbulence, just to get everyone on the same page. Then I'll focus on the coherent structures in turbulent boundary layers, and then specifically in the spectral domain, as opposed to a physical domain. So often both approaches are used. Then in the second part, I'll comment a little bit on the footprint of these coherent structures on the near wall turbulent kinetic energy and talk about some consequences of that. And then a few thoughts on control, just a few very preliminary slides of some thoughts of me, and perhaps they can also set up a bit of conversation here. And then I'll finalize in this third part with a bit of a technical part on the scaling of energy spectra and also the turbulent kinetic energy in high Reynolds number boundary layers. So this first part where I look at the coherent structure, but in the spectral domain, that is quite relevant for the second and third part then, because we use the spectral coherence as kind of a tool in the second and third part. So this is a very quick introduction. For any sort of moving body through a fluid, it triggers this turbulent boundary layer very close to the surface. So these are some of the famous images taken in the 70s and 80s, where you can actually see that very close to the wall, they're primarily small scales active, and they leave this turbulent skin friction at the wall. And then further away from the surface, we have these larger scale motions, which are closer to the edge of this so-called boundary layer. So the skin friction can actually be found from some momentum balance analysis. And one of the relations that exists for that is this Reynolds relation that I just put down here, which is the friction coefficient of this turbulent boundary layer equals, here on the right, some constants and like a Reynolds number. This is a Reynolds number based on the momentum thickness. The skin friction is often expressed also in terms of a friction velocity. So we call the U for velocity, tau for the skin friction, U tau, which is actually defined as this wall friction divided by the density. So that's a scaling parameter for the scales near the wall, so the velocity scaling. And in the outer edge, we have this U infinity. I like to actually think of a ship as, for instance, a flat plate, and often we have a downstream distance x and a free stream velocity. So we can actually define this Reynolds number just based on x. And we can convert that and also get the skin friction then as a function of x, and also the boundary layer growth, delta, as a function of the Reynolds x. And if we have that, we can actually define this new Reynolds number, here the RE tau, the friction Reynolds number, which I will primarily use in this presentation, which is then defined as the length scale delta. So it's the thickness of that layer times or divided by an inner scale, which can be related to the viscosity and the friction of this layer. And so it's the largest scale over the smallest scale at a particular point in that boundary layer. So you can see that typically high Reynolds numbers occur in these practical systems, and with experiments we can go up to the order of tens of thousands of this Reynolds number. And that's a domain I will focus on in this presentation, as it is largely based on some experimental data. Now, why do we study this? Obviously, in sort of layman terms, there's a fuel consumption related to the friction of these turbulent boundary layers. So these are the fuel burns of these transport systems. And because I'm now in the aerospace engineering faculty, this is actually a homework problem I give to students. If they compute with very simple flat plate turbulent boundary layer equations, the drag on a ship, a large container ship cruising, that friction drag actually equals the takeoff weight of a Boeing 737. So that gives you an idea of the magnitude of these friction forces. Okay, so here I'm delving a little bit more in depth in the boundary layer itself. So I'm starting close to the wall, and then I'm moving away from the wall. This is just a very brief review of some of the coherent structures that have been sort of classified over the past 20, 50 years, I would say, in an instantaneous sense. So very close to the wall, we have what they call near wall streaks. These are kind of streamwise vorticity, and they can also form into these vortex filaments that lift away from the wall. So there are some examples here shown on the bottom. Then further away from the wall, there have been a lot of talk about these sort of lifted up vortices that can form these hairpin packets, primarily seen in great DNS work. And then they can also form trains of packets, and that has been really brought forward by the Adrian sort of community here. And then the very high Reynolds number community has also identified these very long elongated structures. This is a plan view of the boundary layer, which are called superstructures. And here the black and white regions are positive and negative velocity fluctuation. So you see these very long streaks that can reach more than 20 times the thickness of this boundary layer. Now, intriguingly, when you actually in Turbulence do statistical analysis, when we look at correlations, very often that whole wealth of structures that I just showed typically condenses to these two-point correlations. So here I show an example from DNS, and here on the right from hot wire data, but you can also create this from PIV data. So both numerics and experiments. And this two-point correlation, you typically take a reference point in the boundary layer, compute the correlation with the 3D surroundings, and you get this sort of this light blue region here, a positive correlation, which is flanked by these two negative correlations. So that shows that it's not completely broadband, so there's some organization. And typically this is also an inclined structure, and that is related to the fact that we have this mean shear in the boundary layer. So there is some spatial lag between what happens at the wall and what happens further away from the wall. Now, even though it's very useful to look at these correlations, what is really sort of lost in these kind of views is a sense of scale and also hierarchy of scales. And that's primarily because we just divide this correlation by the total amount of energy in the signal. So we don't do this in a scale dependent way. And this is really where some of the spectral view or the spectral equivalent of this two-point correlation can be handy and offer some additional insight. And that's what I started doing when I was actually in Melbourne. So this is a bit of a review. I think it's maybe a bit simple for most of us, but I thought also for the students, I do a very quick recap of correlations. Here I'm just considering two signals. My mouse pointer is very slow. I think, is it still visible?
It's still visible. Yeah.
Yes, okay. Now these are two signals, so at different heights in a boundary layer, can be a time or a space signal. And I can do the correlation of these signals in either a physical space or a spectral space. So in physical domain, very simple, if I do that, I get this 2-point correlation curve. So here we have a correlation between 0 and 1 normalized on the vertical axis. And this is then a time or space lag. And here it peaks at a slight offset, which is related to that lag in the boundary layer. So that's what we typically get with this physical correlation for two signals. Then the spectral equivalent is that we really start with the spectra. So here, the top here are the two energy spectra of the signals on the left, where we have here a wavelength, so large scales on the right, small scales on the left. And we can do a correlation where we actually compute the cross spectrum between the two signals. It's a complex value. And if we normalize the magnitude of that by the two individual power spectra, we get this coherence spectrum. So this is the spectral equivalent of this curve on the left here. And here we have again a correlation between 0 and 1 as a function of wavelength. And we see that the small scales are not correlated at all between these two signals. And the large scales up to, in this case, about 80%. So very significant correlation at the very large scales. We also have a phase, actually, of the complex cross spectrum, which I show on the bottom here. I'm not considering the phase really in this presentation, but what I wanted to point out here is that really the coherence spectrum, I interpret that as just a measure of the phase consistency, because obviously if you have a noisy phase for each ensemble of your cross spectrum, then the coherence is 0. And here you can see there's coherence, and suddenly the phase has some consistent trend to it. Okay, so that was just for two signals in a boundary layer, the simplest case possible. So now what I can do in an actual boundary layer, I can have one reference signal, in this case very near the wall, and another signal away from the wall. And I can do that correlation. We just saw this coherent spectrum, which is 0 at the small wavelengths and 80% here at the large wavelengths. I can now do that for different positions of this outer layer probe to kind of compute how each location of that boundary layer is coherent with a wall observer. So this very near wall reference probe. And when I do that, I get the following. So on the right-hand side, I now plot the contour of these coherence spectrograms. So this is now still wavelength on the bottom axis. And here I have the wall normal distance on this vertical axis. And these blue contours are the coherence. So you can see if I slice that contour here, I actually get back this coherence spectrum here on the left. So you see that the small scale energy, that is actually the gray contour, is the energy in the boundary layer of the streamwise velocity fluctuations. You see that that is not correlated with the wall at all, but only the large scales are. So basically the energy that lays below this blue contour. And you immediately also see this trend here. So there's these contours here in the logarithmic region actually follow a slope of 1. Now that can be actually explained by, if we just follow this framework that was put forward by Perry and co-workers. If you say, okay, let's consider the boundary layer as a hierarchy of turbulent scales, the exact velocity fields of these turbulent eddies do not matter, but let's say one hierarchy extends to a certain wall normal distance. Then there's coherence over that wall normal distance of these turbulent eddies. From a certain wavelength forward, because there's no energy at the very small scales of the viscous scales, let's say. So this is this plot here on the left, on the bottom, on the right, sorry, is again the same plane. So we have here a wavelength on this axis, and this is a wall normal distance, and this is that coherence contour of just a single hierarchy. This becomes now a bit more clear if I add a second hierarchy. So I'm multiplying the size of those eddies to a larger scale in a self-similar way. Now these eddies are larger, so they start at a larger wavelength and they extend further from the wall. And if you keep doing that, it actually happens to be equal increments on this plot because it's a logarithmic axis. So you see that this coherence sort of follows this contour if you just follow this simple model here, and that's what the data also shows here. So in this red triangular region, we see exactly what we just constructed here in a very simplified way. And the slope here of this line is equal to 1, and that happens to be at a location that the wavelength equals 14 times the wall normal extent of these eddy structures. So you could interpret that as an aspect ratio, really, where you have some spectral wavelength of these things. So not really physical distance, but more a spectral length scale divided by the wall normal extent. So that is 14 in this case. Now this is only at one Reynolds number. So this was actually data at RE tau of 14,000 acquired in the Melbourne boundary layer wind tunnel. If you follow this framework, it should actually be Reynolds number independent, because the idea is if you go to higher Reynolds number, you just add more and more hierarchy of scales. So the larger scale on the order of delta becomes larger and larger with respect to the smallest scale. Now, if you actually extend this to larger wavelengths here, at some point we hit that boundary layer edge and you cannot really grow these structures anymore. And then at the large wavelength, you see that these contours just flatten out to a wavelength independent behavior. And that's also what we really see in the data. So this is beautifully reflected here in this yellow rectangle here. And I think that is essentially the spectral sort of equivalent to perhaps some of these motions grouping in very large scale motions and superstructures. So the energy behind there is really related to these superstructures, I would say. So yes, as I said, ideally this is Reynolds number independent, and we actually verified that. So that was done in this paper now 3 years ago, where we use a large range of Reynolds number data. This is from a DNS of the group in Madrid at RE tau 2000. We can create the same contour, so the energy contour and the coherence contour relative to the wall. This is all just streamwise velocity. Then I can superpose the Reynolds number data that I showed before from the lab in Melbourne at 14,000. And I can actually go to an extreme Reynolds number case of 1.4 million, where in the atmospheric surface layer data, this group actually collected sonic anemometer data in a synchronized fashion with a wall shear stress sensor. So you can again do these correlations of, in this case, actually the friction velocity fluctuations with the velocity fluctuations in the boundary layer, which gives you this region here. And you see that all these three contours graze this line of this aspect ratio very well, actually. So here we verified that that is Reynolds number invariant over, in fact, more than 3 decades in the Z direction. So that is, I would say, one of the properties of this spectral coherence. I would say we have identified this very beautiful universal scaling with Reynolds number, which is very hard to see actually in these physical correlations. Another property of this spectral coherence here is really that this is dependent on the thermal stratification. So here I just want to point out that this was verified with atmospheric surface layer data in this paper of Dominic Crook, where we looked at the aspect ratio of this line as now a function of stability. So before I only considered neutrally stable conditions, but if you go to an increasing heat convection away from the surface, so going to the right here is more and more heat convection upward in a boundary layer, the aspect ratio actually decreases to about a value of 2, while in the neutral case, it's about 14. And this is actually quite useful to actually identify these sort of aspect ratios of these coherent structures, and also the phase, which I'm not presenting here, because that is used in some of the wind engineering community models to predict dynamic loads on tall structures in atmospheric surface layers. Another property of this spectral coherence is that it's actually very robust. And what I mean with that is we actually verified that in the logarithmic region here, if you would use temporal data or spatial data from DNS or PIV, you get exactly the same result. And that is mainly because at these scales, at these very large scales, the convection velocity is not really scale dependent. And so we can use Taylor's hypothesis without any discrepancy there. I think what is then also nice to point out is another aspect of the fact that this is a very robust sort of metric to look at correlations in boundary layers, because it's a normalization per scale, as I said before. So what I highlight here is on the top, again, the spectral coherence of the energy with respect to the wall, and on the bottom is a physical correlation. So these are these contours of, in this case, time versus wall normal distance of the 2-point correlation in space, or in physical space. Now, in this case, I use a hot wire at the wall, which is, in this case, a fully resolved measurement. If I use instead a hot film at the wall, which typically attenuates the very small scale energy, if I do that here and I flip sort of back and forth, you see that this spectral correlation does not really change because you normalize it with the energy per scale. But the physical correlation suddenly becomes much larger in the case you use the hot film. And that's because you normalize by the total amount of energy. And the energy is smaller in the hot film sensor, the total resolved energy, which sort of bumps up these correlation contours. So especially for experimentalists, I think this is quite useful because it's actually insensitive to sensor attenuation. And in fact, you don't even have to calibrate your hot wires to get this coherence contour. Of course, the energy contour is a different story. I'm not sure if there are any questions at this point, otherwise I'm just gonna move on and wait till the end. No? Then I'm just moving on with part 2, but feel free to interrupt me. So in this part 2, we actually look at what the consequences of this coherence of these large scales throughout the boundary layer from the wall footprint all the way up to the edge. So we look at basically the interaction of these large scales that are mostly energetic here in the outer region, and how do they interact with this inner region here. So we can actually visualize that using DNS, and I use here the data of the group in Spain at RE-tau of 2000. And I'm looking at 2 plane views of the boundary layer. So here we have streamwise direction, and here we have spanwise. And this is a field very near the wall at 4 viscous units, and this is a field in the log region. Now, if you filter both of these fields with the scales that are only coherent, you obviously get this very coherent picture. So here you have the large scale in this field, and here on the left you have the large scales that are present in this near wall field. And this has that coherence of about 80%, these 2 fields. And you can also see that in nature really occurring. This is a picture that was published in a Physics of Fluids article, I believe, of a lake in Geneva, where you have the atmospheric surface layer and you see these sort of streaky structures close to surface that have some sort of large-scale organization to them. Now, the fact that these most energetic large scales have this still pronounced signature at the wall is often referred to as a superposition of energy from the outer region to the inner region. Then aside from that sort of one-to-one correlation in frequency space of the energy, we also have a what I would say is a nonlinear interaction between the outer region and the wall. So in spectral space, you can think of this as we have these large wavelengths that are not only superimposed on the wall, so energy here, but they also influence scales at a much smaller wavelength, so on the order of the near-wall cycle. So that's a nonlinear interaction in terms of the frequencies. And again, I can visualize that here. So on the right-hand side, I still have the same field of velocity fluctuations in the log region. And on the left, I have the near-wall velocity fluctuations, but now I removed the energy that is directly superposed. So this has no, in the energy spectrogram, no energy at the large scales. But still, if you kind of squeeze your eyes, you see roughly some sort of correlation between these two fields. And that's because actually there are patches in this near-wall field where the near-wall cycle is more intense than the average and also less intense than the average. And you can quantify by sort of giving that an envelope. So for instance, if I focus on this region here, you see more intense fluctuations, which is here in red. And in blue, you may have a region of lower fluctuations. So this is really related to the fact that this large-scale footprint on the wall sets a different boundary condition in terms of the friction velocity, and the near-wall cycle really adapts to that. So that's what is kind of referred to as a modulation effect. Now, this was only at the Reynolds number of 2000. Now I'm sketching here, this is just purely a schematic, what happens at, if I increase the Reynolds number by a factor of 10, so going to 20,000. What happens here is I still have these near-wall streaks. In this case, the span-wise separation of those is about 200 per thickness of the boundary layer. This is a plan view. And because these large-scale structures scale on the order of delta, I have these sort of patches, hopefully you can see that, where you have more intense fluctuations and then less intense fluctuations. Now, in these patches, you have a larger friction velocity at the wall, in, for instance, this patch here, relative to this patch here. So what I would say is you actually have, although the mean Reynolds number is 20,000, you can see it as locally, there's a higher friction Reynolds number in these patches that have a very sort of large-scale, high-velocity event sweeping over the wall, leaving a larger skin friction. And then in between, you have the lower Reynolds number, and the average of those is still 20,000. But what's really happening is you get this spread of friction velocities or Reynolds number if you increase the mean Reynolds number. That's how I see this. So we can actually quantify that as well. So that was done in this work here in 2017. And this really sort of this picture I just described really just follows what Chernychenko at Imperial, for instance, describes as a quasi-steady, quasi-homogeneous model where, again, the near-wall cycle adapts to the local large-scale sort of new boundary condition that is set. And here we can see that. So this is the amplitude of the footprint on this axis of the large-scale velocity event. So this is a large skin friction. This is a small skin friction, just on a large-scale kind of time or space. And this is the amplitude of the near-wall cycle. And we see this very well correlation that appears. And this strengthens really with Reynolds number. And the easiest way to see that, I think, is to, again, go to this spectral view. So here we look at spectra. This is the energy, and this is the wavelength. And the blue spectra are taken in the outer region. And I'm increasing the Reynolds number. So what you get is you get more and more large scales going to these darker lines. Now the superposition can be classified as a, or characterized with a gain. So it's related to this coherence. And the gain is 0 at these small scales because they are not really felt at the wall in a correlated sense. And at the large scales, that gain is constant at about 0.4. So if you multiply that gain, which is that dashed dotted line, by the energy spectra, you get the red ones, which are that superposed signature. And that shows, again, that energy of that superposition is just increasing with Reynolds number. So therefore, this effect I described here becomes really intense with increasing Reynolds number. Then I thought I'll throw in a few slides where I just hypothesize a little bit on the consequences of this effect I just described on control. And I do that for two kind of control scenarios. One of them is sort of a passive control for the inner region turbulence. In this case, I consider riblets. And then also an active outer control. So this first part is really kind of inspired by conversations I've had here with my colleague Davide Modesti, who also was in Melbourne and worked on riblets extensively. And most of the work on riblet walls is for the purpose of basically quantifying the drag reduction they can generate. So typically those studies are done with DNS at relatively low Reynolds number on the order of 200 or 400 RE tau. And you get these performance curves of these riblets. So this is a measure of drag reduction on this axis here. And here we get, in this case, a spacing of the riblets, S plus, which is here the span-wise spacing. And there's an optimum, and in this case, at a inner scaled spacing of S plus of 20, where you get a drag reduction. Now, typically, because these studies are done at low Reynolds number, that scale separation is very limited, or it doesn't really exist. And the riblets are scaled to a mean friction velocity. So I was actually wondering what really happens at high Reynolds number, if you still consider a riblet surface, when that near wall cycle adapts following that quasi-steady, quasi-homogeneous idea to these new boundary conditions set by the footprint of these large scales. So that you can model, sort of the first approximation of answering that question is to just simply model that from the data. So the way I do that here is from actually laboratory data. I consider these patches. This is actually in Hotwire, so time space, where within one of these large scale patches, you can compute a new sort of friction velocity. Because if I compute the spectra just in one of these patches, for instance, one of the red patches where you have a higher friction, I get these energy spectra, which are in this case not collapsing on the average one because I'm using the mean U tau to normalize this energy spectrum. I can, though, collapse those condition spectra still if I use a new friction velocity, which I would say is then the friction velocity that is actually the one in that patch. So that way I kind of infer the friction velocity by saying that the near wall cycle adapts to the new boundary condition. So that's an assumption I make here. And what I then really get is kind of a PDF of the friction velocity instead of just a mean friction velocity. So I can model these PDFs of, in this case, the instantaneous friction velocity, again on a large time scale, relative to a mean friction velocity. And what I can do is that I can say, if we take one of these performance curves of a riblet here, on the left, it's actually from actual DNS data, where I have a drag reduction here on the left axis, and this is the scale of the riblet. It was tuned so that the riblet has an optimum performance here at S plus of 20, a spacing at Reynolds number of 400. But what's really then happening is if you now graze this riblet surface with a very high Reynolds number flow, you are actually operating that riblet not only at that S plus of 20, but also away from that optimum because of these large patches of high and low friction velocity. So what is really happening is it's a PDF of this weighting of this curve instead of just the minimum. And when you do that, then obviously if you go to higher Reynolds number, more and more of this curve is being taken into account. And so the drag reduction effect diminishes if you just accept this very simple sort of model and also extrapolation with Reynolds number. So that is shown here. So here I show the Reynolds number of this particular riblet case where I say, okay, it's 100% efficient at the computed field of Reynolds number 400 from the DNS. But then if you model this higher Reynolds number effect, you start to see this diminishing effect. And at a Reynolds number of about 1 million, you get 60% efficiency. I found that still quite high. I was just curious to see with this exercise if that's anywhere between 20% or 99%. But this gives you an idea of how at least this effect of this large-scale superstructure footprint can diminish a near-wall control effect of riblet surfaces. Then I have some thoughts here on outer control. So this was a project we actually started when I was still at Melbourne Uni, where we wanted to do opposition control of the large-scale structures. And the motive for that is really that at high Reynolds number, the bulk of the turbulent kinetic energy production occurs in the log region, which you can see from these profiles here. And if you're able to do opposition control, ideally you reduce the intensity of these structures in the outer region. They also have this reduced footprint at the wall, which may reduce the near wall cycle intensity via that modulation event, and thereby also the turbulent skin friction. So for that, the only thing I really want to say is that this coherence comes into account because we want to do sensing at the wall of these large-scale structures and then actuate upon those in real time. And for that, we can again use in the spectral domain this correlation in terms of a kind of a transfer kernel to do the estimate of the sensing parameter to what is happening in real time, which we then actuate upon. But this is still a project that I believe is continuing in Melbourne, so then I further refer to that ongoing work. Then in the last part of this presentation, that is really a bit on the energy spectra. So far I just looked at the normalized coherence really. Now I'm considering the absolute amount of energy in these boundary layers. And this is work that we recently published in this part 1, part 2 JFM. So that's why I'm actually having this topic here for the seminar, because this was recently published work, although most of it stems from 2 years ago. So yeah, if I actually look at just the streamwise velocity spectra shown here on the left-hand side in this contour, which we've seen before, this is wavelength, this is wall normal distance. Actually, no existing models are present that can predict this at ranges of Reynolds numbers. And the only really prominent school of thought is by Perry, who hypothesized there should be this self-similar region of scales present in the energy spectrogram as a K-1 region, which you can actually get via various arguments, so in the inertial range of scales. A K-1 in a pre-multiplied spectrum is actually a flat region. So here, Nichols in 2005, from one of the first set of high Reynolds number data in the Melbourne tunnel, actually said that it could be this region here, where you have this triangular region. It should follow a wall scaling on the left, so where the wavelength is proportional to the wall normal distance Z, an outer scaling on the right, and then within that triangular region you have a flat part, so a K-1. Now, if this is true, then with Reynolds number, this should again scale up to kind of a larger triangular region, but this has never really been verified, or I have never seen this in papers. And then furthermore, we just identified that the coherence metric actually shows kind of the trends that you would expect from self-similar arguments in this larger triangular region. So that's the region which we kind of identified before with that coherent spectral coherence metric. So now thinking about that larger region, it may be that there is actually other energy present that really obscures a K-1 region, and that has also been sort of noted by other people in the field. So then that also really followed this hypothesized view of a spectrum. This goes a bit more in the fundamentals of a turbulent spectra on the right, where I just present a spectrum at one wall normal position. So it's a slice through this contour here, where I have a wave number here on this axis. So these are small scales on the right, large scales on the left. And it was really hypothesized by kind of this school of thought of Perry that if you go to extremely large Reynolds numbers, this is the picture that should emerge. Namely that you have at the small scales, you have the K-5/3 and also the dissipative end of the spectrum. Then at the large scale end, you have this kind of blue blob of energy from the outer flow motion, so perhaps superstructures, very large scale motions. But then in between, you have this region where you have these self-similar attached eddy scales, which follow both a wall scaling and also an outer flow scaling, really. So that's this region. But that's only if you go to sufficient Reynolds number where you have this scale separation occur. So what is really happening at lower Reynolds number is that this whole spectral picture gets compressed in the horizontal direction. And what you get is really that these two blue regions sort of start to overlap, and this region of self-similar attached eddy scales kind of becomes embedded in the total spectrogram. So if you just look at the raw spectra, I would argue that it's actually very hard to observe a K-1, at least at the Reynolds numbers we are currently at. And also the data really reflect this sort of schematic here on the top. So now the idea is that we can use this coherence as actually a filter to remove the structures in the spectrogram that may mask that K-1. So this is an attempt to actually reveal that attached eddy sort of spectrum. So here a very quick review on how you can use that coherence as a spectral filter. It really just follows actually simple linear stochastic estimation. You can find this in any signal processing book or work of Adrian, where if I have, again, two signals, I can define the spectral correlation between those, or I can define it in a non-normalized way as a kernel. So the kernel is really just a cross spectrum divided by an input spectrum, if I consider the input here at the wall and the output away from the wall. Now, if I have that kernel, that spectral kernel, I can actually make an estimate of the outer region turbulence based on just a near wall measurement. And the energy of that estimate, so here the estimate is the phi hat, the energy spectrum, equals the kernel squared times the input spectrum. And with a little bit of rewriting, you can write that as actually the coherence between these two probes times the raw measurement at that position. So what you can really do is you can say the energy in that outer region location, if you multiply that by the coherence, you're just left with the energy that is correlated with the reference position. So it's kind of a decomposition that you can do, where I say, okay, we have a raw energy spectrum here on the left, and you can define that into a part that is wall incoherent. So the fraction of 1 minus the coherence spectrogram plus the coherence times that spectrum. So I illustrate that here on the bottom right. raw spectrogram is this gray line here. And then if I multiply that by the coherent spectrogram, I'm just left with this lighter blue spectrum, which is coherent with the wall, and then the other one is incoherent, so in a statistical sense. And if you integrate that, you actually get the respective portions of the turbulent kinetic energy. So we saw before that this coherence was actually Reynolds number invariant, which means it followed this wall scaling. But now if you actually cut through these blue contours perpendicular to that red line, you see that sort of increase of the coherence going to larger scales, which is presented here on the left bottom. And that is also universal. So not only the point where that coherence starts, but also the ramp up. Because here I'm superposing DNS and atmospheric surface layer data. So 3 orders of magnitude apart, and they all collapse. So therefore, I can really take this as a universal filter to apply to spectra of DNS lab data or atmospheric surface layer data to essentially decompose the wall coherent energy from the energy that is incoherent with the wall in a statistical sense. Now, to bring this one step further, the wall coherent energy both includes self-similar motions, but also what is envisioned to be these very global modes that are correlated throughout the entire boundary layer, but that do not scale in a self-similar way anymore. So these are more these superstructures in spectral space. So to separate those two components from one another, we can actually add a second reference probe, and I do that here in the edge of the log region, which kind of, if I flip back and forth, splits this part into 2 contributions, namely one that is smaller than the edge of the log region, and then one that is correlated with the edge of the log region and beyond. And so that kind of brings me to the following picture. Hopefully I kind of recollect everyone on this slide. This is the following picture that we can actually define now a filter from the data as follows. So this is on the left-hand side here, I'm just considering this Reynolds number. We have scale on the bottom axis. So this is small scales, these are large scales. And this is really a fraction of the energy between 0 and 1. And we have these 3 regions, so 2 blue regions and then this white region in between. So the right region here, this blue region, is really the incoherent small scales in a statistical sense. This corner on the left bottom are the larger scales that are going beyond the log region. So I would say they are global scales. And this white part, this fraction of energy, is really these self-similar motions that could occur. And the red part is really just the actually the height of this white region. And this is a low Reynolds number. Now I can define this filter for any Reynolds number because we saw from the data that we have these known scalings. So if I go to very high Reynolds number here on the right for 1 million, you see that the scale separation sort of pulled away these 2 blue regions and opened up this white region where you now have energy that is basically the whole fraction of the energy spectrogram. So 100% of the energy could be related to wall coherent motions up to the edge of the log region, so self-similar scales. So there we could perhaps see a K-1 in the energy spectrogram. And from this scaling, we actually see that the transitions of where we do not have enough scale separation yet, and we do have enough scale separation, happens at about 80,000 following this analysis. So that suggests that if there happens to be a K-1 in the raw spectrum, you have to go to about 80,000 in order to see that. And that is quite, that condition is quite consistent with work that has been done at high Reynolds number, looking at 2-dimensional energy spectra from streamwise, span-wise data. That is actually really the correct way to look at it. So in some sense, all this work is a little bit simplified by just considering 1D spectra. But it still results in these sort of similar conditions that we can derive. Now, even though we're perhaps not with current data at these Reynolds number to get this sufficient scale separation to look at a k-1, we can still do this scale separation or this scale decomposition. So here I do that on the left for an actual spectrum. So this is a spectrum at Reynolds number 14,000 at a Z plus location of 100. And I have these three contributions. Now this small scales, it's this most blue region. I have this red region, and then I have this very large scale motion contribution. And I can actually do this for different Reynolds numbers now. So this is all at a Z plus location of 100. These three different contributions where I increase the Reynolds number from 2000 to about 19,000 from fully resolved measurement. And what you can see is this small scales is quite consistent over this full Reynolds number range, so it collapses. This is a wall scaling on the horizontal axis. This outer layer energy follows a outer scaling, which I'm actually not showing here, but they collapse if you plot it in outer scaling. And in these remaining part really that we try to reveal grows with increasing Reynolds number. And we're not there yet that it really saturates. And that's what you can see from this plot. If I just pick the maximum of the maximum amplitude of these red energy spectra versus Reynolds number, it increases. And it remains actually an open question whether that really plateaus or not. These red points are data from Melbourne, and then the gray points are actually data where I performed this decomposition on the Princeton superpipe data. And there's a bit of a mismatch, probably because of some are due to different computing friction velocity and also the way the measurements are resolved actually. But we don't know yet whether this really plateaus or not. Then finally, I have one slide here on the fact that we can actually now also get a bit more insight into the scaling of turbulence kinetic energy by following this idea of this decomposition. Because if you integrate the spectra, you get back the turbulent kinetic energy. And so you can now do that for the three individual spectra instead of the entire spectrum. So that's the idea here. I'm plot here on the left-hand side the turbulent kinetic energy on the y-axis. I'm starting here with this wall coherent part versus wall normal coordinate. And in the log region, it follows this slope actually, which that constant is known as a Townsend-Perry constant. It's a logarithmic slope. And that is close to about 1. So that's this contribution of energy here to the total turbulent kinetic energy profile, which is kind of roughly this shape, if you recall that from standard boundary layer sort of plots. Now, that follows this logarithmic scaling, really. If I look at the small scales, that actually increases, the energy increases with wall normal distance. So it's not constant, it increases. And that's actually because the dissipation end of the spectrum sort of starts to deviate more and more from a wall scaling. And you can model this contribution of these small scales by just integrating a model spectrum, Kolmogorov spectrum. And if you do that, you get this relationship here. So it's actually scaling with z to the power minus 0.5. So that's this contribution here, which increases in energy if you go towards the right. And then we are left with this contribution from the very large scale global motions. And for that, we really do not have any kind of model for that. So that remains a big question mark. But what we can see is that that typically has this sort of parabolic shape here, where it peaks somewhere in the geometric center of the log region, if you believe that the log region starts at a fixed viscous scale up to a fixed scale in boundary layer thickness. So that's kind of this contribution here. But what I really want to point out is that if you kind of want to fit a line to the turbulence intensity to find, for instance, this contribution of self-similar attached eddies, which should follow a logarithmic slope, it may be misleading to do that to the raw one if you're not at sufficient Reynolds number because of these other contributions not having a constant contribution over this wall normal range. So yes, that brings me to the concluding remarks here. So we have looked at really correlations of boundary layer turbulence, but more in the spectral space. From that, we can derive kind of filters to decompose spectra. And from that, we saw that we have to go at least to a Reynolds number of 80,000 to perhaps see a K-1 appear. Then, so that is still inconclusive really with the data we have presently or currently available. And then there is some evidence that if you do this decomposition, that you get a Townsend-Perry constant that's actually appears at all Reynolds numbers of about a value of about 1. And that could also be the amplitude of this K-1 where we're not there yet. So yes, that finishes the talk. So thank you so much. I would like to acknowledge the people here who have been co-authors and colleagues on some of the works presented here. And then I would like to just end with the schematic. Hopefully some of the organizers of this seminar are not having this thought for the one scheduling next week after listening to this one. So thank you so much.
Thank you. Thanks so much for that talk. So we do have time for some questions. If people, you can simply unmute and ask your question, or you can put your hand up in the participants list and I can call on you. So.
Yeah, let me ask a question. Very nice work, nice lecture that refreshed our understanding of neural coherent structures. Okay, speaking of footprints of the neural turbulent structure, well, shear is one thing, right? Which could be used for direct reduction study. Mm-hmm. But another footprint arguably is a wall pressure, right?
Yes.
So probably there's more related to like vertical fluctuation rather than streamwise fluctuating velocity. Have you looked at or do you have any plan to look at the wall pressure? I mean, application is obviously the sound generation. Mm-hmm. From turbulent boundary layer, right?
Yes, yeah. I have personally not looked at these wall pressure velocity correlations, but likely indeed the wall pressure has more of a large scale content. So I think that you can quantify again quite nicely in the spectral domain as well, which I haven't done experimental wise. I think some data exist. I could also do it from the DNS data that is publicly available, but I've not looked into it. It is interesting because at least in one of the projects here, where I'm more going towards some active control of boundary layers on airfoils, we want to actually use wall pressure as an input for control. So then mm-hmm. a pre-step to sort of, for instance, do real-time active control of turbulence is to quantify really the pressure velocity coupling. Mm-hmm. I did look up some papers, so some beautiful papers exist on that work, but I think mainly at the lower Reynolds number sort of DNS data.
So am I correct in saying that if you have three components of, the fluctuating velocity components,
yes,
you can actually deduce the wall pressure spectra, right? If you have a three component velocity, can you actually compute the pressure on the wall?
Oh, for wall pressure reconstruction, I think you could do that from DNS data if you have the full 3D field. Yes.
Or any really
using some Poisson equation idea, I think. Yeah.
Fine-grained even measurement too, right? If you have a really
correct
high resolution, high resolution measurement, you can, in principle, you can compute the wall pressure. Yeah, that will be interesting because, of course, I mean, you know, the equilibrium boundary layer, probably people don't worry too much about noise or sound generation, but there's interest there, at least academic interest as far as I'm concerned. Okay, thank you.
And then for instance, for input on real-time control, I think the easiest would be just to mount a pressure microphone behind a pinhole in a plate, because that just gives you the time pressure or the time signal of pressure, which is a very robust actually measurement if you go to real practical systems where you don't maybe want to measure the fluctuating skin friction, for instance, on the outside of a plane.
Thank you very much. Thank you.
Sure.
Okay, do we have any other questions? I might just ask a quick question while people are gathering their thoughts. So you mentioned, I mean, all the work that you were showing, as you mentioned, was kind of these 1D energy spectrums. And you did have one line mentioning 2D. And I was wondering what do you expect that to appear in the 2D energy spectrum that's not really covered here?
Yeah, actually, I think the work on that, I think it's, maybe some of the Melbourne people have to fill me in on that. It's either being published or is just published. It's really Dilip Chandran and is working on that at Melbourne Uni. But really, if you look at energy, for instance, in a wall parallel plane, it is really distributed in spectral space in both the streamwise and span-wise wave numbers. So if you do this correlation between two different heights, I'm basically integrating the 2D spectrum along span, and that is the data I'm dealing with because I have 1D data. But to do this correctly, you have to preserve also the span-wise wave number dependence. I don't have a picture here of these 2D spectra, but then instead of just a 1D spectra becomes 2D, and the coherence actually becomes also 2D. So you could do that. I at that time that I did this sort of work, I just didn't have the data. From DNS, I had the 2D spectra, but not experimentally. So now in Melbourne, they have focused quite a lot with hot wire measurement to get these 2D spectra at high Reynolds number. Yeah.
Thanks.
I'm not sure if the authors of those papers are in this video call, but
it might be. The participants list is a bit long to kind of scroll through, but yeah, that's good. Any other questions? All right. Otherwise, I think we might leave it there. Thank you again, Woutijn, because that was a pleasant talk, and everyone else will hopefully see you in a week's time. Okay.
Okay. Thank you, everyone.
Great talk.
Thank you. Good to see everyone on the other side of the world. Have a good day.
Magic of modern technology.
Bye-bye.
Take care. Bye-bye. Thank you.